Alright, hi, I'm Brandis. I'm here to spread the word of the derivative, and you're gonna learn today. So I'm just trying to make a visual representation of what the derivative is and how you can understand it and how you can use that to do problems if you're taking calc in school. So, alright, let's say you have this graph. I'm gonna call it f of x, and you can think of this graph as sort of, if this is, this x-axis is time, and this y-axis is height. You can think of this as the graph of a ball that's being thrown up and comes right back down. So let me just have a little example. Here's my little ball. So it goes up, 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 up. It sort of stops for a second and then it comes right back down. And this graph is the representation of that as its height and its time. So let's take an example of the ball. It's going up, and let's say 1 second after it goes up, it's at the height of, let's say 2. So let's say at time 1 in seconds, it has a height of, say, 2 meters in meters. So the question that the derivative is asking is, okay, well, I know the ball is right here. Oops. The ball is at 2 meters once 1 second has passed. But the question that they're asking is, how fast is the ball going? And what we're going to do in the next video is understand what that means graphically and what that means through math. And we're going to figure out the answer to that question if we have the function of distance and time. So yeah. Alright, I hope you guys are excited because we're about to invent calculus. You should be hyped. I'm excited. So we're just going to get started, alright? So, here I have a point right here, and I'm going to say this is the point where we're going to try and calculate the derivative, where we're going to try and find the instant velocity of the ball at this point. So the same statements, right? So I'm going to say this point is 1, 2, okay? Now, we're trying to figure it out. We don't really know how to find the instant velocity, but we can find the average velocity if we have another point. So I'm going to say, okay, I see another point right here. It's 3, 4, right? So let's start by calculating the average velocity between those 2 points. And that's easy. It's just the rise over the run. So it's the change in y over the change in x, which is just 4 minus 2 over 3 minus 1. And that's just 2 over 2, which is just 1. So what does this 1 mean? Graphically. It means, okay, if you were to draw this line called the secant line between these 2 points, the slope would just be 1, because that's the rate of change. And it means that between 1 second and 3 seconds of the ball, the average velocity is 1 meter per second. That's what it means. So, okay, we understand how to get the average velocity, but we're trying to find the velocity at that point. So we don't really want a point that's super far away. We want it to get closer and closer to it. So why don't we try taking the velocity of a closer point? So we want to keep our 1, 2, but let's try a closer point. Let's say 2, 3 right here. I'm making these things up, but okay. Oops. Our rise over our run again. It's going to be taking this one, since it's a little farther, 3 minus 2. Oops. Yeah, 3 minus 2 over 2 minus 1. Just be 1 over 1. It's just 1. That's just me picking dumb numbers. It's not supposed to be like that, but and again, that's just the slope of this line. So we understand how to find the average velocity between any 2 points. And our goal is to make, if this point, is static, we want this point to be closer and closer and closer to it so that we can find the tangent line at that point. All right, so we're gonna try and like visualize that, what I just said. So we have this point A on the x-axis, and that's our fixed point. We're trying to find the derivative at A. And we have another point on the graph, which is gonna be x on the x-axis, because it's gonna start changing and flipping around, and things like that. So we wanna keep it free. So A on the y-axis corresponds to f of A, because you know we have the function f of x. You just plug in A. And the same thing for f of x. Can be anywhere. So if we want to find the secant line between these 2 points, we would just do what we've been doing, but we're trying to make it more general. So the slope of this line would just be the rise over the run, like we talked about. Oops. Which is just, okay, the rise being the change in y, f of x minus f of A, and the run is going to be the change in x, which is going to be x minus A. But our goal is to find the tangent line here, right? So we don't want a tangent line, a secant line where x is far away from A. We want a secant line where x is moving closer and closer to A. And how can we represent that? Well, if you watched my previous videos, you'd know this thing about limits, where you can compute that. So our goal, when we want to find the tangent line, is to compute the limit as x is heading to A of this entire function, of f of x minus f of A over x minus A. And this will give you the slope of this tangent line. And it will also give you the derivative of f of x at A. So all of these are saying the same thing. And, wait, we're not done yet. The instantaneous velocity of our ball at a second, sort of. That's what it means in terms of like the real world, you know? So all these things are saying the same thing. They're all the same. So we just invented calculus. Like, pat yourself on the back. We did a great job.